Every textbook on Earth says the universe expanded at a specific speed after the Big Bang. Scientists spent 50 years building that number. They checked it with satellites, with supernovas, with ancient light. They were certain. Then two different teams measured the same number and got two completely different answers. A Nobel Prize winner looked at the data and said, out loud, "Our model of the universe is broken. We will go through dark energy changing, galaxies that should not exist, a force of nature nobody named yet, and what it all means for reality itself." If you enjoy this journey, subscribe and hit like. Let's go. The ceremony was supposed to be a celebration. It was 2011. A scientist named Adam Rees stood on a stage in Stockholm, Sweden, receiving the most respected prize in science, the Nobel Prize in Physics. He had earned it by discovering something that shook the entire field. The universe, he proved, is speeding up. Every galaxy flying away from every other galaxy, faster and faster, with no end in sight. The crowd applauded. The cameras flashed. The science world called it one of the greatest discoveries of the modern era. But Rees kept working. He kept measuring. He kept checking. And slowly, quietly, a problem started growing inside the data that nobody wanted to talk about. Here is what happened. Scientists have a number they use to describe how fast the universe is expanding right now. Every measurement, every telescope, every satellite eventually feeds into this one figure. Get it wrong, and every map of the cosmos, every prediction about the future of galaxies, every calculation about what happened after the Big Bang falls apart. Rees measured that number using exploding stars billions of light years away. His team spent years refining the method. They checked it over and over. The answer they kept getting was around 73 kilometers per second per megaparsec. You do not need to memorize that. Just picture it as a speedometer reading for the entire universe. Then, a completely separate team used a totally different method. They studied ancient light left over from the Big Bang itself, light so old it predates every star and planet. Their answer came back as 67 kilometers per second per megaparsec, 6 units apart. That sounds small. It is enormous. 6 units in this context means the universe is expanding roughly 8% faster than the oldest measurements predict it should be. Picture 2 GPS systems, both trying to find your house, using completely different satellites, and one tells you to turn left while the other tells you to turn right. One of them is wrong, or the map itself is wrong. For a few years, scientists assumed it was a math error. Someone miscounted. Someone's telescope was slightly off. These things happen. The error never appeared. Teams around the world spent years searching for it. They found nothing. The gap stayed. Both sides kept refining their tools, and both sides kept getting the same disagreeing answer. That gap now has a name, the Hubble tension. And in recent years, Rees himself began saying it out loud at conferences, in papers, in interviews. The model is broken. These are not the words of a fringe scientist. This is a Nobel Prize winner, one of the most decorated astronomers alive, looking at the best data humanity has ever collected and saying something is fundamentally wrong with the way we understand the universe. Physicists call this kind of moment a crisis, a point where the old explanation stops working and something new has to take its place. The last time cosmology had a crisis this big, Einstein rewrote the laws of gravity. The question now is, what breaks first? The measurements, the math, or everything we thought we knew about space, time, and how the universe began? Because whatever the answer is, it changes everything built on top of it. And the strangest part of this story has barely started. For decades, there was one idea that held the entire field of cosmology together. Scientists called it the standard model of cosmology. Some call it lambda CDM, but you can think of it simply as the textbook version of the universe. It was the framework every space mission used. Every telescope was built to test it. Every equation about the age, size, and future of the cosmos ran through it. For roughly 30 years, it worked beautifully. Here is what it says. The universe started with the Big Bang, about 13.8 billion years ago. In the first fraction of a second, space itself expanded at an almost impossible rate, spreading everything outward. Over billions of years, gravity pulled hydrogen clouds into stars. Stars burned and exploded into heavier elements. Those elements clumped into planets, and here we are. The model also says the universe is made of three main ingredients. About 5% is ordinary matter. Everything you can see, touch, and measure. Planets, stars, gas clouds, you. The rest is invisible. About 27% is dark matter, a kind of mass that pulls things together but gives off no light. The remaining 68% is dark energy, a force pushing everything apart, driving the universe's expansion. That breakdown, 5, 27, 68, is the recipe the model uses to explain everything from the movement of galaxies to the temperature of ancient light. And for a long time, every single measurement matched. Scientists used satellites to map the oldest light in the universe, called the cosmic microwave background. It looked exactly like the model predicted. They counted galaxies across billions of light years. The pattern matched. They watched how galaxy clusters formed, and where they clustered still matched. The standard model passed test after test after test. So, scientists trusted it completely. That trust had consequences. When you trust a model that completely, you stop questioning the assumptions baked into it. You stop asking whether the 5 ingredients are really right. You stop wondering whether the rules you applied to the early universe still work the same way today. And that is exactly where the crack appeared. The model was built in 2 separate stages. The early universe part came from studying ancient light with extreme precision. The later universe part came from watching stars and galaxies directly. When scientists combined both stages into one picture, everything lined up until it didn't. The moment those 2 stages gave different answers for the expansion rate, the entire model came under pressure, because the model was designed to describe one single, consistent universe. A universe where the rules stay the same from the beginning to now. If the early part gives one number and the late part gives another, then somewhere in between, something changed. And if something changed, the model missed it. A model that misses something that big is incomplete at best, flat out wrong at worst. What makes this genuinely alarming is how long the model took to build. Generations of scientists spent their careers constructing it. It passed hundreds of independent checks, and still, something slipped through. Scientists now have to figure out whether the crack is in the measurements or in the model itself. The answer to that question will determine the next 100 years of physics. And what they found when they started pulling on that crack goes much deeper than anyone expected. There is a single number at the center of this entire crisis. Scientists call it the Hubble constant. It measures how fast the universe is expanding right now, at this moment, everywhere at once. Every point in space is moving away from every other point. Galaxies are not flying through space. Space itself is stretching, like a rubber sheet being pulled from every edge. The Hubble constant tells you the speed of that stretch. Picture every galaxy as a dot drawn on a balloon. You blow the balloon up and every dot moves away from every other dot. The Hubble constant is the number that describes how fast you are inflating that balloon. Get that number right and you can calculate the age of the universe, its size, its future, and the exact mix of matter and energy inside it. Every major question in cosmology runs through this one measurement. Edwin Hubble, the astronomer the number is named after, first measured it in 1929. His tools were primitive by today's standards. His first estimate was off by almost a factor of 7 compared to what scientists know now. But he established the idea: the universe is expanding, and it expands at a measurable rate. For decades, scientists fought about the correct value. Different teams, different telescopes, different methods, all giving slightly different answers. By the late 1990s, the field had mostly settled. The number landed somewhere around 70 units, and most scientists agreed that was close enough. Then two things happened that blew the agreement apart. The first was that measurement tools got dramatically better. Satellites launched, space telescopes went up. Scientists could measure things to a precision that Edwin Hubble could not have imagined. And the better the tools got, the more the two main methods of measuring the Hubble constant disagreed. The second thing was that nobody found a flaw in either method. Team 1 measures the expansion rate using the oldest light in the universe. This light, called the cosmic microwave background, spread across all of space, roughly 380,000 years after the Big Bang. Scientists can model exactly how that light should look if the standard model is correct. When they compare prediction to observation, they get a Hubble constant of 67.4 units. Team 2 builds what is called a cosmic distance ladder. They measure distances to nearby stars, then use those distances to calibrate measurements to farther stars, then farther galaxies, then galaxy clusters billions of light years away. At every step, they use different types of stars as measuring tools. Their number comes back as 73 units. 67 versus 73. That is a gap of about 9%. In everyday life, 9% sounds manageable. In cosmology, it is a 5-alarm fire. The measurements are precise enough that this gap cannot be explained by random error alone. Scientists have calculated the odds of both teams being right and the gap being a coincidence. Those odds are roughly 1 in a million. One of the methods is picking up something real, something the model never predicted. And the longer the gap refuses to close, the more likely it becomes that the something is not an error at all. It is a discovery. Something happened to the universe between its earliest moments and today. Something that accelerated its expansion beyond what the standard model allows. Nobody knows what it is yet. But the next clue came from light 13 billion years old, and it pointed somewhere nobody wanted to look. Imagine looking at the sky and seeing light that left its source before Earth existed, before the sun existed, before a single star had formed anywhere in the universe. Light so ancient it carries the fingerprint of the universe, just 380,000 years after it was born. That light is real. Scientists call it the cosmic microwave background, and it became one of the most powerful tools in the history of science. Here is how it works. Right after the Big Bang, the entire universe was a dense, blazing hot soup of particles. Everything was packed so tightly that light could not travel more than a tiny distance before smashing into something. The universe was opaque, like trying to see through a wall of steam. Then, about 380,000 years in, the universe cooled just enough for electrons and protons to combine into hydrogen atoms. Suddenly, the fog lifted. Light could travel freely for the first time. It shot outward in every direction and has been traveling ever since for over 13 billion years. Today, that ancient light has stretched so much, cooled so far, that it is no longer visible to the naked eye. It lives in the microwave range, far below what human eyes can detect. But satellites can detect it. And when scientists mapped it across the entire sky, they found something extraordinary. The light is almost perfectly smooth, nearly the same temperature in every direction. But embedded in it are tiny ripples, temperature variations of about 1 part in 100,000. Too small to feel, too small to see, but absolutely critical. Those ripples are the imprints of sound waves that traveled through the early universe. When matter and energy were packed together, pressure waves moved through the cosmic soup like sound moves through water. They left a pattern, and that pattern is frozen into the ancient light we can still detect today. Scientists used a satellite called the Wilkinson Microwave Anisotropy Probe, and later the Planck satellite, to map those ripples with extreme care. The Planck satellite, launched in 2009, spent 4 years collecting data. It gave humanity the most detailed map of the ancient light ever made. From that map, scientists could calculate exactly how fast the universe must have been expanding at the very beginning. and project that forward to figure out the expansion rate today. The number they got was 67.4 units. This number is incredibly precise. The error bars, meaning the range of uncertainty around the answer, are smaller than 1%. That is tighter than almost any measurement in all of science. The result matched the standard model so well that many scientists considered the question settled. But the moment another team went out and measured the expansion rate using a completely different method in the nearby universe, the settled answer started looking less like a triumph and more like a warning no one had noticed yet. Because the ancient light was telling one story, the modern universe was telling another, and both stories were backed by decades of work, thousands of researchers, and billions of dollars worth of equipment. They cannot both be fully right. And the scarier possibility, the one scientists are now taking seriously, is that they actually are both right, and the universe changed in between. What the second team found, using dying stars as cosmic rulers, shook the entire field. In 1998, two separate teams of astronomers were racing to answer one of the biggest questions in science. Was the universe's expansion slowing down? Everyone expected the answer to be yes. Gravity pulls things together. After the Big Bang, all that outward energy should be bleeding off. The universe should be decelerating, like a ball thrown into the air that slowly loses speed before falling back down. Both teams were measuring the brightness of a specific type of exploding star. These explosions are called Type Ia supernovae, and they are remarkable tools. Every single one of these explosions releases almost exactly the same amount of energy, every time, without exception. That makes them work like a cosmic measuring tape. Picture a flashlight. If you know exactly how bright that flashlight is, you can figure out how far away it is just by measuring how dim it looks from where you're standing. The dimmer it looks, the farther away it must be. These exploding stars work the same way. Scientists know their true brightness, so measuring how dim they appear tells them exactly how far away they are. And here is where everything went wrong, in the best possible, most world-shaking way. The distant exploding stars were dimmer than they should have been. Way dimmer. That meant they were farther away than the models predicted. The universe had not been slowing down at all. It had been speeding up. The expansion of the universe is accelerating. That discovery won Adam Rees and his colleagues the Nobel Prize. It completely overturned the expected picture of the cosmos. Something was pushing the universe apart faster and faster. Scientists named that something dark energy. They had no idea what it was. They still don't. But they plugged it into the standard model, and the model kept working. Rees and his team kept using exploding stars to refine the expansion rate. They built an incredibly careful measurement chain. First, they measured distances to nearby stars using a method called parallax, the same principle your two eyes use to judge depth. Then they used those distances to calibrate pulsing stars called Cepheids. Then they used the Cepheids to calibrate the exploding stars. Each step locked in the next. After years of refinement, their number settled at around 73 units. That is almost 9% higher than the 67.4 coming from the ancient light. For a while, both sides assumed the other had a systematic error buried somewhere, a miscalibration, a wrong assumption, something that, when found and fixed, would make the numbers agree. But the numbers never agreed. Both teams kept getting better. Their error bars kept shrinking, and the gap between them stayed wide open. By the time astronomers started taking this seriously as a real crisis rather than a measurement problem, they gave it a formal name, the Hubble tension. And the tension was about to get much worse, because the tool that was supposed to solve it, the most powerful space telescope ever launched, pointed at the same stars and made the gap bigger. By 2019, the Hubble tension had officially become a crisis. That word, crisis, means something specific in science. It describes a situation where multiple high-quality experiments run independently by separate teams using different methods keep producing results that contradict each other and refuse to reconcile. A crisis is not a mistake. It is a signal. It means the model is missing something real. The two numbers, 67 and 73, were now backed by enormous amounts of data. The team measuring ancient light had used two of the most carefully built satellites in history. The team using exploding stars had spent over a decade cross-checking every step of their method. Independent groups had replicated both results using completely different instruments. Both answers kept coming back the same. Scientists calculated the statistical tension between the two measurements. In physics, tension is measured in units called sigma. 1 sigma means the gap could plausibly be a coincidence. 2 sigma means it's unlikely. 3 sigma means something is almost certainly real. 5 sigma is the gold standard for a confirmed discovery. The Hubble tension reached 5 sigma. That means the odds of the gap being a random accident are about 1 in 3.5 million. 5 sigma is the same confidence level used to announce the discovery of the Higgs boson, one of the most celebrated moments in modern physics. The Hubble tension now carries that same statistical weight, and what it is pointing to has no agreed-upon answer. Something is genuinely wrong. 3 possible explanations exist, and none of them are comfortable. The first is that one of the measurements has a hidden flaw, something so subtle it survived years of checking. A wrong assumption buried so deep inside the math that nobody caught it. This is the most hopeful answer. It means the standard model survives, and scientists just need to find the mistake. The second possibility is that both measurements are correct, and the universe actually behaves differently in different epochs. The early universe obeyed one set of rules. The universe today obeys a slightly different set. Something changed in between, something the model never predicted and cannot explain with its current ingredients. The third possibility is the one that keeps physicists up at night. Both measurements are correct. Both eras of the universe are being read accurately, and the standard model itself is wrong. A new framework is needed, one that can contain both numbers, explain why they differ, and still account for everything the old model explained correctly. Each of those options would reshape physics. The first would add a correction to an otherwise working model. The second would require an unknown event or substance added to the middle of cosmic history. The third would mean that the equations used to describe the universe for 3 decades need to be replaced. And here is the part that makes this genuinely strange to sit with. Every other test of the standard model still passes. Galaxy formation matches the predictions. The ratios of hydrogen and helium in the universe match. The geometry of space on large scales matches. Only this one number refuses to fit. One crack in an otherwise perfect wall. And the man who discovered the universe was speeding up was already convinced that crack goes all the way through. The next part of the story begins with Adam Rees, a whiteboard full of measurements, and a decision to go public with something the field had been quietly dreading. When the Hubble tension first appeared in the data, almost nobody panicked. That sounds surprising now. But in science, small disagreements between measurements are completely normal. Instruments drift, calibrations slip. Someone makes an assumption early in the analysis that seemed reasonable at the time but turns out to be slightly off. These things happen constantly. They get found, fixed, and the field moves on. So, when the 2 expansion rate measurements started giving different answers in the early 2000s, the almost universal response was, someone made an error. Find it, fix it, move on. Scientists call this kind of hunt a systematic error search. You go back through every step of both measurements and look for anything that could nudge the answer in the wrong direction. Wrong star temperatures, miscounted distances, inaccurate brightness estimates, even subtle effects from dust in our own galaxy bending or reddening light from distant stars. For the team measuring ancient light, the checks were exhaustive. They reanalyzed the satellite data multiple times. They cross-checked their map of the cosmic microwave background against predictions from dozens of different theoretical models. They looked for instrument errors, data processing errors, modeling errors. Nothing turned up. For the team using exploding stars, the checks were equally thorough. The question of whether the pulsing stars called Cepheids were being measured correctly became a years-long investigation. Cepheids brighten and dim in a regular rhythm. That rhythm directly reveals their true brightness. And if you know their true brightness, you know their distance. But what if something in the environment around those stars, dust, gravity from nearby stars, crowded star fields, was subtly skewing the measurements? Teams around the world attacked that question from every angle. They used different types of stars to calibrate distances. They looked for Cepheids in cleaner, less crowded regions of space. They applied new computer models to strip out the effects of dust. Every check they ran either confirmed the original measurement or made the tensions slightly worse. By around 2019, after roughly 15 years of systematic searching, the scientific consensus shifted. The error is probably not there. The tension is probably real. Whatever is causing the two numbers to disagree is probably a feature of the universe itself, not a flaw in the measurements. That shift in consensus had enormous implications. Because if the error is in the universe and not the math, it means the universe does something the standard model says it should not do. It expands at a rate today that is not consistent with how it should have evolved from the early state we can measure so precisely. Something changed, something intervened, something pushed the expansion faster than predicted, and nobody had a name for it yet. Nobody had a mechanism. Nobody had even a sketch of what kind of physics could produce this specific result. What they had was a number that refused to budge, two methods that refused to agree, and the growing realization that the disagreement was pointing somewhere genuinely unknown. The next step was to bring in the most powerful tool humanity had ever pointed at the sky, hoping it would finally settle the debate. It did the opposite. Adam Rees does not look like someone who broke the universe. He is a soft-spoken professor at Johns Hopkins University in Baltimore. He runs a research group. He teaches classes. He answers emails. But in the late 1990s, Rees was part of one of the most dramatic discoveries in scientific history. His team was measuring distant exploding stars to figure out how much the universe's expansion was slowing down. Everyone expected a slowdown. Gravity decelerates things. The numbers should have reflected that. Instead, the stars were too faint, too far. The universe was accelerating. Something was pushing it apart faster than it had any right to go. Rees and his collaborators named that something dark energy and published their findings. The field was stunned. 13 years later, Rees stood in Stockholm to collect a Nobel Prize. He could have stopped there. He had earned his place in history. He kept going. After the Nobel, Rees threw his lab's full energy into refining the cosmic distance ladder, the chain of measurements used to calculate the expansion rate of the nearby universe. He and his team, called SHUIS, which stands for supernova, and H0 for the equation of state of dark energy, spent years improving every link in that chain. They gathered data from the Hubble Space Telescope for decades. They measured pulsing stars in dozens of galaxies. They compiled the most careful, most checked, most independent set of distance measurements ever assembled. Every time they refined something, they expected the final number to move closer to 67 and ease the tension. Every time, the number stayed near 73. By 2019, Rees published a paper with a title that was blunt enough to make the physics world stop scrolling. He described the tension as reaching a level where the chances of it being a statistical accident were roughly 1 in 100,000. He argued publicly that the standard model needed new physics to survive. New physics. That phrase carries enormous weight. It means the current equations, the current ingredients, the current framework are incomplete. Something exists in the universe that the model has no room for. Rees began giving talks at conferences saying exactly that. He described the disagreement between the two measurements, not as a puzzle waiting to be solved with better instruments, but as a doorway, a crack in the wall of the standard model through which something genuinely new was trying to get in. His position put him in direct, respectful tension with cosmologists on the other side who trusted the ancient light measurements and believed the distant star results contained an undiscovered error. The debate became one of the most watched arguments in modern astrophysics. And then the James Webb Space Telescope launched. Both camps believed it would end the debate. Webb was 10 times more powerful than anything before it. It could see stars in environments that the older Hubble telescope could barely resolve. It would find the error, if there was one. Reese knew what was at stake. So did the entire cosmology community. They waited months for the first Webb data to come back, and when it did, the room got very quiet. On December 25th, 2021, a rocket lifted off from a launch site in South America, carrying the most expensive, most complex, most anticipated scientific instrument ever built by human beings. The James Webb Space Telescope had been in development for 26 years. Its construction cost $10 billion. It involved the work of 10,000 engineers, scientists, and technicians across 14 countries. The telescope's mirror, made of 18 gold-coated hexagonal segments, stretched almost 22 feet across, too wide to fit inside any rocket fairing in one piece. Engineers had to fold it like origami and trust it to unfold perfectly in the cold of space. If a single hinge failed, the entire mission would be lost. Over the next month, Webb traveled almost 1 million miles from Earth, slowly unfolded itself, cooled its instruments down to temperatures colder than the surface of Pluto, and began capturing light from the earliest galaxies in the universe. The scientific community held its breath for most of it. Webb was built partly to answer a specific question about the Hubble tension. The Cepheid stars at the heart of Adam Rees's distance measurements had always been observed in relatively crowded star fields. Critics argued that nearby stars could be blending their light with the Cepheids, making them look slightly brighter and therefore slightly closer than they actually are. If Cepheids were being measured as too close, the final expansion rate would come out too high. The tension might disappear. Webb could see individual stars in galaxies far enough away that no previous telescope could cleanly separate them. If the crowded field problem was real, Webb would find it. Rees was actually open to being wrong. He said so publicly. If Webb found the systematic error, that would be a good result. It would mean the model was intact. He would have been part of finding the correction. Science would move forward cleanly. The first Webb results on Cepheids came back in early 2023. The crowding problem was real. Webb found it immediately. Stars in the Cepheid fields were indeed blending their light in the older Hubble images. Critics felt vindicated for about 48 hours. Then the numbers came back. After correcting for the crowding effect using Webb's sharper vision, the distance measurements barely changed. The correction was real, but small. The effect on the final Hubble constant was negligible. The numbers still came back near 73. The gap was still there, fully intact. Rees and his team published the results within weeks. The conclusion was direct. The tension survives contact with the most powerful telescope ever built. The crowded field problem, the most promising candidate for a systematic error in years, turned out to be a minor correction with no power to close the gap. The Hubble tension was now more solid than ever, but Webb was just getting started, and what it found next had nothing to do with Cepheids. It had to do with galaxies that should not exist, and those galaxies would crack the model open from a completely different direction. After the Cepheid results confirmed the tension was real, Adam Rees's team kept pushing Webb to go further. They pointed the telescope at galaxies farther out than any previous distance measurement had reached clearly. The goal was to add more rungs to the cosmic distance ladder and see if the expansion rate kept coming back at 73, or whether it shifted at greater distances. The ladder is exactly what it sounds like. You measure nearby things first, then you use those measurements to reach slightly farther, then farther again. Each rung depends on the one below it. Nearby star distances are measured by watching how those stars appear to shift slightly against the background sky as Earth orbits the Sunday. That shift gives a direct geometric distance measurement, no assumptions needed. From those nearby stars, scientists calibrate Cepheid variables. Those pulsing stars can be seen in galaxies tens of millions of light years away. From the Cepheids, scientists calibrate the exploding stars. Those explosions can be seen billions of light years away. And from the exploding stars, scientists calculate the expansion rate. The fear has always been that an error in one rung, even a small one, multiplies as you climb higher. A 1% error in the lowest rung can become a 5% error by the time you reach the top. Webb was meant to check whether the lower rungs were clean. Webb checked them and found that Rees's team had been doing it right. The parallax distances, the Cepheid distances, and the exploding star distances all lined up correctly when Webb re-examined them with its sharper resolution. The measurements were consistent at every rung. The ladder was sound. The number at the top of the ladder was still 73. Meanwhile, the other side of the measurement, the ancient light side, was also producing new results. Scientists reanalyzed the Planck satellite data with updated models. They added new datasets from ground-based telescopes that measure how large-scale galaxy clusters move. Every analysis kept returning the same answer, 67.4. Two independent, thoroughly checked, technically sound measurements, still 9% apart. By 2024, some of the scientists who had spent years searching for an error quietly admitted there was probably no error to find. The conversation in the field shifted from "let's find the mistake" to "let's figure out what new physics this is pointing at." That shift felt different. A mystery with a hidden error is frustrating. A mystery with no hidden error is thrilling and terrifying at the same time. Because now the question was no longer about instruments or math. The question was about the universe itself. What could make the expansion rate behave differently across cosmic time? What kind of ingredient, what kind of event, what kind of force could produce exactly this specific discrepancy and nothing else? Several answers started emerging from the physics community. Each one was stranger than the last. And the one that gained the most traction involved something scientists had already named but never fully understood. Something that makes up 68% of everything in the universe, drives its acceleration, and remains completely invisible: dark energy, and the possibility that it is changing. In 1998, when Adam Rees and his colleagues discovered the universe was accelerating, they needed a name for whatever was driving it. They borrowed one: dark energy. The name sounds dramatic. It is also almost entirely a placeholder. Dark energy is the label scientists put on a force that makes up roughly 68% of everything in the universe, drives the expansion of all of space, and cannot be directly detected, measured, touched, or seen. Scientists know it exists because of what it does. They have almost no idea what it actually is. Picture the universe like a balloon being inflated. Gravity, the attraction between all matter, should be slowing that inflation down, but the balloon is actually speeding up. Something is inflating it from the outside. That something is dark energy. In the standard model, dark energy is described by a single number called the cosmological constant, which scientists label with the Greek letter lambda. It represents a fixed, unchanging energy density spread evenly through all of space. Every cubic inch of the universe, no matter where you look, contains the same amount of this energy, and that energy pushes space outward. The cosmological constant model is elegant. It requires only one number to describe an entire cosmic force, and for about 20 years, the data seemed to support it. But a fixed cosmological constant also makes a specific prediction. If dark energy is constant, it pushes the universe apart at a steady, predictable rate throughout history. The expansion rate you calculate from the early universe should match the expansion rate you measure today, after accounting for how matter and gravity have behaved in between. That prediction is exactly what the Hubble tension destroys. The gap between 67 and 73 is precisely what you would expect to see if dark energy did something unexpected at some point in cosmic history. If it was weaker in the early universe and grew stronger later, or if it fluctuated, or if it interacted with something else in a way the model does not account for. A fixed, unchanging dark energy cannot produce that gap. So either the gap is wrong, and every team checking it has missed the same error for 20 years, or dark energy is not fixed and unchanging. And here is where it starts to feel genuinely unsettling. If dark energy can change, then the future of the universe becomes dramatically less predictable. A constant dark energy produces a steady, slow expansion that ends with galaxies drifting apart over hundreds of billions of years, cold and quiet. A changing dark energy could accelerate that process. It could, depending on how it changes, lead to something physicists call the Big Rip, where the expansion grows so fast it eventually tears apart galaxies, then solar systems, then planets, then atoms. The difference between a gentle cosmic fade and that outcome depends entirely on the behavior of dark energy, and scientists have just found the first real evidence that dark energy might be doing something the standard model says it cannot. That evidence came from a survey so large it mapped 38 million galaxies, and what those galaxies revealed made the cosmological constant look very fragile. In April 2024, a team of scientists published results from the most ambitious map of the universe ever completed. The project was called the Dark Energy Spectroscopic Instrument, and it had spent 5 years scanning the sky from a mountaintop in Arizona. The instrument pointed at roughly 38 million galaxies and measured not just where they were, but how fast they were moving and how their positions had changed over billions of years. The goal was to track how dark energy behaved through different eras of cosmic history. If dark energy is constant, its effect on galaxy movement should look the same whether you examine the universe from 8 billion years ago or from today. Constant means constant. The results showed something different. When the team analyzed how galaxy clusters moved and clustered across different time periods, the pattern did not fit a constant dark energy. The data matched better with a model where dark energy is weaker in the past and grows stronger over time, not dramatically. The signal was at about 2 to 3 sigma, not yet at the 5 sigma level needed to call it confirmed. But it was there, and it pointed in a very specific direction. Dark energy might be evolving. If that is correct, the cosmological constant is wrong, not slightly off, structurally wrong. An evolving dark energy means the universe does not have a fixed energy density spread through space. It means that density changes, the force changes, and a changing force makes predictions about the future of the universe enormously more complicated. Picture the expansion of the universe as a car on a highway. A constant dark energy means the accelerator is pressed to a fixed position. The car speeds up, but at a predictable rate. An evolving dark energy means someone is slowly pressing the accelerator harder. The car is speeding up faster than the speedometer prepared you for. If dark energy grows strong enough, eventually nothing can hold the universe together. Gravity loses, galaxy clusters separate, then individual galaxies, then solar systems, then planets. Then, at the very end, atoms themselves get torn apart. The Big Rip scenario gives Earth a destruction date of roughly 22 billion years from now if certain models of evolving dark energy are correct. That is a long time from now, vastly longer than the current age of the universe. But the point is not the timeline. The point is that a universe with evolving dark energy is a fundamentally different universe from the one the standard model describes. And there is more. An evolving dark energy also changes the expected expansion rate across cosmic time. Some models of evolving dark energy naturally produce an expansion rate in the early universe that looks like 67, and an expansion rate today that looks like 73. In other words, evolving dark energy might be the answer to the Hubble tension. The two mysteries could be one mystery. That possibility sent the field into a new level of excitement, and it brought back one of the most famous equations in the history of science, written by a man who once called it his greatest blunder. Albert Einstein introduced the cosmological constant in 1917. He was trying to solve a problem that had nothing to do with the accelerating universe, because no one knew the universe was accelerating yet. Einstein's problem was simpler and, at the time, urgent. His equations of general relativity, the theory describing how gravity bends space and time, predicted that the universe should be moving, either expanding or collapsing. But the scientific consensus in 1917 was that the universe was static and eternal. Einstein did not want his equations to predict motion, so he added a term to balance them out, a constant value, spread through all of space, that pushed outward just enough to counteract the pull of gravity and hold the universe still. He called it the cosmological constant. It worked mathematically. The equations balanced. The universe sat still, on paper. Then, in 1929, Edwin Hubble showed that the universe was expanding. Einstein's static model was wrong. The universe was moving after all, and the cosmological constant, the fix Einstein had introduced to keep it still, was suddenly unnecessary. Einstein reportedly called the cosmological constant his greatest mistake. He removed it from his equations. Then, 69 years later, Rees and his team discovered the universe was accelerating, and that acceleration needed exactly the kind of outward-pushing, space-filling energy term that Einstein had added and then removed. The cosmological constant came back. In modern cosmology, it represents dark energy, a fixed, unchanging energy spread through all of space, driving expansion. It is now the central feature of the Standard Model. The lambda in lambda CDM, the framework that has governed cosmology for 3 decades, is literally Einstein's biggest mistake repurposed and placed at the heart of the field, and now it is under pressure again. The problem with the cosmological constant is subtle but severe. Quantum physics, the science of tiny particles and forces, predicts that empty space should be filled with energy from particles constantly popping in and out of existence. The predicted value of that energy, using the equations of quantum physics, is roughly 10 to the power of 120 times larger than the cosmological constant that actually fits the astronomical data. That mismatch between quantum prediction and observed value is one of the greatest unsolved problems in all of physics. Scientists call it the vacuum catastrophe. The constant that Einstein originally invented to keep the universe still, and that now explains its acceleration, requires a value that quantum mechanics cannot explain at all. If dark energy is evolving, the cosmological constant model collapses entirely. A new theory of dark energy takes its place, and several candidates are already being seriously debated. The leading one has a name that sounds like something from a fantasy novel, but the physics behind it is rigorously real, and it changes the picture of dark energy from a static ingredient to a living, shifting field that moves through the universe like a wave. In the early 2000s, a group of physicists proposed an idea that turned dark energy from a fixed background into a dynamic character. They called it quintessence. The name comes from ancient philosophy, the idea that a fifth element, beyond earth, water, fire, and air, fills the universe. Physicists gave it a modern meaning, a field that exists everywhere in space and carries energy that changes over time. The cosmological constant treats dark energy like a property of space itself. A room has a temperature, empty space has an energy density, fixed, everywhere, always the same. Quintessence treats dark energy as a field, more like an ocean than a temperature. And oceans have waves, they shift, they push harder at some times than others. The technical difference matters enormously. A cosmological constant has what physicists call an equation of state value of exactly -1. That number describes the relationship between the energy and pressure of dark energy. A value of exactly -1 is perfectly consistent with a constant, unchanging force. Quintessence models predict a value that is slightly different from -1, and that changes over time. In the early universe, the field sits at one value. As the universe ages, the field shifts. The energy it carries can grow or shrink. The push it exerts on space is not the same at every moment in history. This sounds like a technical detail. The consequences are massive. If quintessence is real, the expansion rate of the universe is not a smooth, predictable curve. It has variations built in. The rate at which space expanded 13 billion years ago is genuinely different from the rate at which it expands today, driven by changes in the quintessence field, not just by how matter has diluted over time. That difference is exactly what the Hubble tension is measuring. The Dark Energy Spectroscopic Instrument results from 2024. The ones pointing toward evolving dark energy fit comfortably with certain quintessence models. The equation of state value the survey measured was slightly above -1 in the early universe and shifting, exactly the kind of behavior quintessence predicts. Scientists are not saying quintessence is confirmed. The data is not yet strong enough to rule out a cosmological constant entirely, but the direction of the evidence is consistent, and several independent lines of data are now pointing the same way. The practical consequence for the Hubble tension is significant. A quintessence field that was weaker in the early universe and grew stronger over time would cause the expansion to accelerate in a specific pattern. That pattern would make measurements of the early universe, using ancient light, return a lower expansion rate, and measurements of the nearby universe, using exploding stars, return a higher one. 67 in the past, 73 today, exactly the gap that has resisted explanation for 20 years. Quintessence does not solve the problem completely. Scientists need to explain why the field takes the specific form it does, why it changes at the rate it does, and what drives the change. Those answers do not exist yet, but the next clue came from a direction nobody expected. A possible fifth force of nature, hiding inside the same gap the telescopes had been staring at for decades. Physics recognizes 4 fundamental forces. Gravity holds planets in orbit and keeps your feet on the ground. Electromagnetism powers every light, screen, and electrical device on Earth. The strong nuclear force binds the particles inside atomic nuclei together. The weak nuclear force governs radioactive decay. These 4 forces explain essentially every physical process scientists have ever observed. The standard model of particle physics, separate from the cosmological standard model but deeply connected, is built on them. Together they form the theoretical backbone of modern science. Now, a growing group of physicists believes there might be a fifth. The Hubble tension is one reason. The gap between the 2 expansion rate measurements has a very specific size and shape. Some physicists noticed that the gap is hard to explain with changes in dark energy alone. An evolving dark energy can shift the numbers, but getting them to shift by exactly the right amount, in the right direction, without disturbing other measurements that are working perfectly, requires precise fine-tuning. A fifth force offers a different route. If a new force exists that acts on dark energy, or on the matter in the universe, in a way that the 4 known forces do not, it could naturally produce the exact gap the Hubble tension describes. The force would have to be extremely weak and operate only on cosmological scales, meaning it would affect the universe as a whole but be far too subtle to detect in any laboratory on Earth. That last point is why this idea is so difficult to test. Every experiment ever run to look for new fundamental forces has been done in labs, on Earth, or in the solar system. A cosmological force, one that only becomes meaningful across distances of hundreds of millions of light years, would be completely invisible at those scales. Its absence from laboratory experiments would mean nothing. A team at Princeton University ran detailed computer models in 2022, examining whether a specific type of fifth force, one that changes the effective strength of gravity on cosmic scales, could explain the Hubble tension. Their models showed that certain versions of this force produced expansion histories, matching the observational data better than the standard model alone. Other teams pushed back. They argued that adding a fifth force without direct evidence is a drastic step. Physics has a principle, sometimes called Occam's razor, that says you should not add new entities to an explanation unless they are necessary. A fifth force is a very large new entity. But necessity is exactly what the Hubble tension is creating. After 20 years, after Webb, after 38 million galaxies, after every systematic check in the book, the gap is still there. And a gap that refuses to close starts demanding answers that go beyond the existing toolkit. Scientists disagree about whether a fifth force is the answer. What they agree on is that the existing four are not enough to explain what the data shows. And that is before you account for what might have happened in the very first moments after the Big Bang. Because some physicists believe the Hubble tension does not point to something happening today. They believe it points to something that happened at the very beginning, before any star had ever formed, something that fired off once, set the universe on a slightly different trajectory, and then vanished. Most of the explanations for the Hubble tension focus on what is happening now: a changing dark energy, a new force, something in the current universe that is making the expansion rate higher than the ancient light predicts. But a separate group of physicists took a different approach. They asked, what if the problem did not start now? What if it started in the first, second, after the Big Bang? Their idea is called early dark energy. Here is the concept. The standard model assumes dark energy has always been present at roughly the same level, a constant background. But what if, in the first moments of the universe, there was a brief surge of extra energy, a pulse that lasted only a fraction of the universe's early history, boosted the expansion rate during that window, and then faded away? If that pulse happened before the ancient light we use for measurements was released, it would have altered the size of the early universe in ways that are difficult to detect. The ripples in the ancient light, the pattern scientists used to calculate the Hubble constant, depend on the size of the universe at the moment the light was released. A slightly different size would produce a slightly different ripple pattern, and that different pattern would make the ancient light team calculate a higher expansion rate. Higher, not lower. Wait, the ancient light gives 67, the nearby stars give 73, so the ancient light team is already getting the lower number. Early dark energy would raise their number. That means early dark energy might actually help the two sides agree, because it would push the ancient light measurement upward towards 73. Several research groups published models of early dark energy between 2019 and 2023. Some of those models worked remarkably well. They could match the ancient light data with a modified early universe and produce a Hubble constant near 73, removing most of the tension. There was a catch. Early dark energy models fix the Hubble tension but create new problems elsewhere. When scientists plug early dark energy into the full standard model and run simulations of how galaxies form and cluster, the results do not match observations as well as the original model. The distribution of matter in the universe, how clumpy or smooth galaxies are on large scales, comes out slightly wrong. Trade one problem for another. This is where the search for an explanation gets genuinely hard. Every candidate that resolves the Hubble tension seems to break something else in the model. The model is tightly connected. Pull one thread and another loosens. Some physicists call this the Hubble tension hydra. Cut one head and two more grow back. Early dark energy is still on the table. Researchers are working to refine the models, find versions that fix the tension without breaking the galaxy clustering. Some teams believe there is a version of early dark energy that threads the needle correctly. But to understand why every solution creates a ripple effect, you have to understand how deeply connected the standard model's pieces are. And that starts with understanding what happens when you make one wrong assumption at the very beginning of everything. The consequences of that single wrong assumption cascade across 13 billion years of cosmic history. And the story of how one mistake at second zero of the universe could still be causing headaches for scientists today is stranger than almost anything the tension has produced so far. The standard model of cosmology is a chain. Each piece connects to the piece before it and the piece after it. The conditions of the early universe determine how it evolved. The way it evolved determines what we can measure today. The measurements today are used to confirm the early universe conditions. Round and round, the model checks itself through this loop. The strength of this chain is also its greatest danger. If one link is wrong, everything downstream of it is also wrong, and the older the mistake, the farther it propagates. Imagine you are building a map of a city. You start with a single reference point, one street corner whose exact coordinates you are certain of. From there, every measurement branches outward. Every block, every intersection, every building gets its position relative to that original point. If your original coordinate is off by even half a degree, by the time you have mapped 50 city blocks, the entire east side of your map is in the wrong place. The local measurements look fine, but zoomed out, the city is warped. Cosmology works the same way. The universe, at the Big Bang, is the starting reference point. Every equation that describes what came after flows from the conditions at that moment, the temperature of the early universe, the density of matter and energy, the rate of initial expansion. Every one of those values feeds into the next calculation. Scientists believe they know those starting conditions extremely well. The ancient light maps from the Planck satellite gave them precision down to fractions of a percent. The Standard Model's predictions for the first few minutes of the universe match observations of hydrogen and helium in today's cosmos almost perfectly. The early universe seems well understood, but almost is doing a lot of work in that sentence. If one early universe parameter is off by a tiny amount, something too small to detect directly in the ancient light, the error builds over 13 billion years of cosmic evolution. The universe today would look almost exactly like the models predict. Every measurement would pass. Every galaxy cluster would form roughly where expected. Almost everything would check out, except one number. One stubborn, high-precision number measured two different ways by two independent teams would refuse to agree. The Hubble tension fits that description perfectly. Some physicists have proposed that the density of particles called neutrinos in the early universe was slightly higher than the Standard Model assumes. Neutrinos are nearly massless particles that barely interact with anything. They flooded the early universe in enormous numbers. A small change in their count would alter how fast the early universe expanded. That altered expansion rate would feed forward through 13 billion years and change what the modern universe's expansion rate looks like to a distant observer. The neutrino count the Standard Model uses was set based on measurements made decades ago with instruments that were good but not perfect. There is room, a small but real room, for the actual count to be slightly different. Other physicists have proposed that the effective number of particle species active in the early universe was slightly higher than assumed. This falls under a parameter called the effective number of relativistic species, which sounds technical but means essentially how many types of fundamental particles were energetically active right after the Big Bang. A few more than expected would change the early expansion rate in exactly the direction needed to reduce the Hubble tension. None of these proposals have been confirmed. All of them are being actively tested with new data, but the underlying message is the same. If the universe was born slightly different from the textbook version, the discrepancy we see today is exactly what you would expect. One wrong assumption, 13 billion years. One crack in a model that was otherwise perfect, and the tool built to find that crack just found something even harder to explain. Every measurement astronomers make of the distant universe starts with a chain. Scientists call it the cosmic distance ladder. It is not a metaphor for a general process. It is a literal, step-by-step sequence of measurements, where each rung depends on the accuracy of the one below it. Break any rung, and every measurement above it becomes unreliable. The bottom rung is the most solid. It uses pure geometry. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of far more distant stars, the same way your finger seems to jump left and right when you close one eye and then the other. That shift is called parallax. Using basic trigonometry, scientists can calculate the exact distance to any star close enough to show a measurable shift. No assumptions needed, just angles and math. This method works reliably out to about 3,000 light-years from Earth. The nearest star outside our solar system is about 4 light-years away. The parallax method handles it easily. Stars a few hundred light-years out, also fine. Beyond 3,000 light-years, the shift becomes too small to measure accurately, even with the best instruments. So scientists move to rung 2. Pulsing stars called Cepheid variables sit on this rung. These stars brighten and dim in a rhythm that reveals their true luminosity. The slower the pulse, the more intrinsically bright the star. Scientists can see Cepheids in galaxies tens of millions of light-years away, far beyond the reach of parallax. By comparing how bright a Cepheid looks from Earth against how bright it actually is, scientists calculate the distance. But to trust Cepheid distances, you have to trust your calibration of the relationship between their pulse rate and their true brightness. That calibration comes from Cepheids close enough to measure directly with parallax. The lower rung feeds the upper one. From Cepheids, scientists reach rung 3. These are the exploding stars called Type Ia supernovae, visible across billions of light-years. They are calibrated using galaxies where scientists can measure both Cepheid distances and supernova brightness at the same time. Those galaxies become calibration anchors. From the supernovae, scientists measure the expansion rate of the universe across cosmic distances, the final number on the ladder. The entire chain spans roughly a factor of 1 billion in distance, from a few light-years at the bottom to billions of light-years at the top. A factor of 1 billion amplifies errors dramatically. A 1% miscalibration in the Cepheid rung does not stay at 1% by the time it reaches the top. It can shift the final expansion rate measurement by several percent. Critics of Adam Riess's 73 measurement have pointed at every rung looking for that miscalibration. Dust near Cepheids absorbing light. Crowded star fields blending light. Cepheids in different chemical environments pulsing differently than expected. All of these have been investigated thoroughly. The Webb results addressed most of them. The ladder held. But there is another way to measure cosmic distances that bypasses Cepheids entirely. And when scientists built that alternative ruler and measured the same galaxies, they got an answer that was close to 73, but not identical. The fact that two distance methods, both independent of ancient light, give slightly different answers from each other, raises a question that nobody has fully answered yet. What if the problem is not the instruments at all, but the space the light travels through? Henrietta Swan Leavitt discovered one of the most powerful tools in astronomy in 1912. She was working at the Harvard Observatory, cataloging thousands of stars from photographic plates. She noticed something that changed cosmology forever. A specific type of star, one that regularly brightens and dims over days or weeks, followed a precise rule. The longer the cycle, the more light the star actually produced. Always, without exception. It was a built-in brightness label, embedded in the star's own behavior. These stars are called Cepheid variables, named after the first example discovered, a star in the constellation Cepheus. And for over a century, they have served as the primary measuring sticks for cosmic distances. The logic is elegant. You observe a Cepheid in a distant galaxy. You measure how long its brightening cycle takes. That tells you its true brightness. You compare true brightness to apparent brightness, how dim it looks from Earth, and geometry does the rest, distance calculated. Leavitt's discovery let Edwin Hubble measure the distance to galaxies in the 1920s and prove that the fuzzy patches in the sky, called nebulae, were actually entire galaxies, millions of light-years away. She handed humanity its first ruler long enough to measure the cosmos. But a ruler used for over 100 years accumulates questions. The central concern scientists have raised in the context of the Hubble tension involves the environments where Cepheids live. Leavitt calibrated her relationship using Cepheids in the Small Magellanic Cloud, a small companion galaxy to our own. Those stars lived in a relatively sparse, clean environment. The Cepheids Adam Riess's team uses to anchor the cosmic distance ladder live in the disks of large spiral galaxies. These are dense, crowded environments full of dust, gas, and other stars. Dust absorbs and reddens light. Crowded star fields blend the light from neighboring stars with the Cepheids' light, making it look brighter than it actually is. A Cepheid that looks brighter than it is will be calculated as closer than it actually is. A distance measurement that is too short produces an expansion rate that is too high. That concern is legitimate. It drove much of the motivation for using Webb's sharper vision on Cepheid fields. Webb found the crowding issue was real. Stars were blending, but when scientists corrected for it, the distances barely moved. The correction was smaller than the critics had hoped, far too small to close the Hubble tension. A second concern involves the chemical makeup of Cepheid stars. The pulse-brightness relationship Leavitt found was assumed to be universal. A Cepheid is a Cepheid, but more recent research suggests the relationship shifts slightly depending on how many heavy elements the star contains. Stars in chemically different environments pulse with slightly different relationships between cycle length and true brightness. Rees's team has applied corrections for this effect. They have tested Cepheids in multiple different galaxy types and chemical environments to build a calibration that accounts for the variation. Critics argue the corrections might not be complete. Rees's team argues the corrections are thorough and the data is sound. The argument has not been settled to everyone's satisfaction, and the fact that it has not been settled kept pushing the field toward an alternative distance method, one that sidesteps Cepheids entirely. That alternative uses stars at a completely different moment in their lives, stars at the edge of a specific death, and the story of how that ruler was built leads somewhere the Cepheid debate never quite reached. When a star roughly the size of our Sun runs out of fuel in its core, it does not die immediately. Instead, it swells. The outer layers expand enormously. The star becomes a red giant, cool and enormous, thousands of times larger than it was before. Our Sun will eventually do this. In about 5 billion years, it will puff out to roughly the size of Earth's orbit, swallowing Mercury and Venus, and possibly Earth along the way. During this swelling phase, helium accumulates in the star's core, helium ash from the hydrogen burning above it. As the helium builds up, the core compresses and heats. Then, at a very specific temperature and pressure threshold, something sudden happens. Helium ignites. The core erupts in a brief nuclear explosion called the helium flash. The star settles into a new, smaller, hotter configuration and never returns to its red giant form. The critical detail is the threshold. Every star that goes through this process ignites at nearly the same core temperature and pressure. Stars of slightly different masses and chemical compositions all hit essentially the same trigger point. This means that at the moment, just before the helium flash, all red giant stars reach nearly the same maximum brightness. It is a natural ceiling, a brightness limit set by nuclear physics. Astronomers call it the tip of the red giant branch. And because every red giant reaches the same peak brightness before its helium ignites, scientists can use them as distance markers, the same way they use Cepheids or exploding stars. You know the true brightness. You measure the apparent brightness. Distance follows. This method has a major advantage. Red giants are everywhere. Every old star cluster and every old galaxy contains hundreds of them. They are abundant, bright, and reliably calibrated by the same nuclear physics regardless of their environment. Dust affects them differently than it affects Cepheids. The measurement chain is largely independent. Several teams have used the tip of the red giant branch method to calculate the Hubble constant. Their results have been interesting and complicated at the same time. Most of these measurements land in a range of about 69 to 72 units. That is lower than Rees's 73, but higher than the Ancient Light's 67, sitting directly in between. Some researchers interpreted this as evidence that Cepheids are slightly overestimating distances, making Rees's number a bit too high. They argue the true late universe expansion rate is closer to 70, and that a measurement around 70 would reduce but not eliminate the Hubble tension. Others argue the red giant method has its own calibration uncertainties. The exact brightness of the tip depends slightly on the age and chemical composition of the star population, and those corrections are harder to pin down than they appear. The result of having multiple distance methods that give slightly different answers within the late universe measurement is telling in its own right. It suggests the ladder is not perfectly understood at every rung, and it raises a deeper question. What if distance in the universe is not as straightforward as the models assume? What if space itself, the medium the light travels through, behaves differently depending on where in the cosmos you are measuring? That question leads somewhere genuinely strange. The standard model treats the universe as homogeneous. That word means the same everywhere, at large enough scales. Zoom in and you see galaxies, clusters, voids, filaments, structure everywhere. But zoom out far enough, the model says, and the universe becomes smooth. Every large patch of space looks like every other large patch. Same density of matter, same laws of physics, same expansion rate. This assumption is called the cosmological principle. It is baked into every equation that describes the universe as a whole. The ancient light measurements assume it. The distance ladder calculations assume it. The standard model runs on it. But what if it is wrong? Scientists know the universe is not perfectly smooth, even on large scales. Galaxy surveys over the past 3 decades have revealed structures that stretch hundreds of millions of light years across. Massive walls of galaxies, giant voids where almost nothing exists, filaments connecting galaxy clusters like threads in a cosmic web. These structures are far larger than anyone expected when the cosmological principle was established. The key question is whether these structures are large enough to affect measurements of the expansion rate. If Earth sits inside or near the edge of a region of space with a slightly lower than average density of matter, that region would expand slightly faster than the universe's average rate. The local expansion rate, the number you would measure using nearby galaxies and exploding stars, would be higher than the global average. Precisely what Rees's team is seeing. This idea has a name. Physicists call it the local void hypothesis. The idea that our galaxy, the Milky Way, lives in a slightly underdense bubble of space, and that bubble's faster expansion is inflating the local Hubble constant measurement above the true cosmic average. Some surveys have found evidence of a mild underdensity in our local cosmic neighborhood, a region roughly 600 million light-years across, sometimes called the KBC void, that contains somewhat fewer galaxies than the cosmic average. The debate is whether the void is deep enough, wide enough, and well measured enough to account for a 9% difference in the Hubble constant. Several teams have argued the void effect is real, but too small to close the gap on its own. Other teams have argued the void is larger and deeper than the surveys suggest. This connects to the disagreement between distance methods in a direct way. If local space is genuinely underdense and expanding faster, then measurements made in that local region, using any method that relies on nearby galaxies, would return an inflated expansion rate. Cepheids, red giant tips, and supernovae all live in this local region. They would all read slightly high compared to the cosmic average. The ancient light measurement does not. It samples the entire observable universe from the beginning of time. It does not care about local underdensities. If the local void is real and large enough, both measurements could technically be correct. They are measuring different things: local expansion versus global expansion. But that explanation has its own uncomfortable consequence. If different regions of the universe expand at different rates, then the cosmological principle itself is wrong. The universe is not homogeneous at the level the model requires. And if that principle falls, the entire framework built on top of it needs to be rebuilt. Something far stranger than a single number being wrong. In 2014, a team of astronomers mapped a structure in the universe that should not have existed. They called it the Hercules Corona Borealis Great Wall. It is a concentration of galaxies connected by gravity and proximity that stretches roughly 10 billion light-years from end to end. 10 billion light-years. The observable universe is about 93 billion light-years across. This single structure spans more than 1/10 of it. The standard model sets a limit on how large structures in the universe can grow. Based on the speed of expansion and the age of the cosmos, gravity has had a limited amount of time to pull matter together. Structures beyond about 1.2 billion light-years should not exist. There has simply not been enough time, at the expansion rates the model predicts, for gravity to connect matter across larger distances. The Hercules Corona Borealis Great Wall is 10 times that limit. Scientists debated the discovery intensely. Some argued the statistical analysis was flawed and the structure is less coherent than it appears. Others argued it is real and represents a genuine violation of the homogeneity the standard model requires. It is not alone. The Sloan Great Wall, discovered in 2003, stretches over 1 billion light-years. The Giant Arc, announced in 2021, spans about 3.3 billion light-years. A structure called the Big Ring, found in 2024 by the same team that found the Giant Arc, stretches over 1 billion light-years across and forms an almost perfect circle in the sky, a perfect ring of galaxies, 1 billion light-years wide, arranged in a circle. No known physical process in the standard model forms that shape the existence of these structures matters for the Hubble tension in a very specific way. If the universe contains structure on scales the model says should be empty, then the assumption of homogeneity is wrong at a fundamental level. And if homogeneity is wrong, every calculation that uses it to interpret measurements could be off. Distance measurements assume light travels through a statistically uniform universe. If the light from distant exploding stars passes through a massive underdense void or through a dense wall of galaxies on its way to our telescopes, those structures bend and stretch the light in ways that are difficult to correct for. A measurement that does not account for the large-scale structure the light passed through will give a slightly wrong answer. Whether the wrong answer goes high or low depends on the specific geometry of the path the light traveled. Different sightlines through different structures would give different results, and that would mean different measurement teams, pointing their telescopes in different directions, would get systematically different answers, not because their instruments disagree, but because the universe itself is not uniform. This remains an open area of research. No one has proven that known large-scale structures account for the full Hubble tension. But the structures are there. They are bigger than the model says they should be, and they are the right kind of problem to produce exactly the type of measurement inconsistencies the field has been wrestling with for 2 decades. And there is one specific structure, discovered by mapping the motion of our own galaxy, that is more bizarre than any wall or ring found so far. Galaxies are not sitting still. The Milky Way is moving. Right now, at roughly 1.3 million miles per hour relative to the ancient light background. For decades, astronomers have been mapping the gravitational sources pulling our galaxy in that direction. A massive concentration of galaxies called the Great Attractor sits roughly 250 million light-years away and pulls our galaxy toward it. Beyond that, an even larger structure called the Shapley supercluster adds its pull. That much was known. But in 2017, a team of astronomers realized something was missing from the equation. The pulls they had catalogued were real, but not enough. Our galaxy was moving faster toward the Great Attractor direction than the known gravitational sources could explain. Something else had to be involved. They mapped the distribution of galaxies in the opposite direction and found what they were looking for. In the direction the Milky Way is moving away from, there is an enormous void. An underdense region of space, roughly 800 million light-years across, where the expected density of galaxies is far lower than the cosmic average. A void does not have gravity to pull. It has an absence of gravity, and that absence pushes, in the same way that a vacuum cleaner does not pull dirt toward it, as much as the higher pressure air around it pushes the dirt in. The void creates a lower pressure region in the gravitational landscape, and our galaxy, along with thousands of nearby galaxies, flows away from it. The team called this structure the dipole repeller. The name is precise. It actively repels our galaxy. The Milky Way is being pushed by a cosmic absence, a hole in the structure of the universe, as much as it is being pulled by the visible concentrations of matter. The dipole repeller sits in the direction of the Gemini and Canis major constellations. It is 800 million light-years across. To put that in terms closer to home, the distance from Earth to the Sun is about 93 million miles. 800 million light-years contains an almost incomprehensible number of those distances stacked inside it. And the dipole repeller is mostly empty. The existence of this structure has direct implications for the Hubble tension. If our galaxy sits near the edge of an enormous void, and that void is pushing local galaxies outward, then measurements of nearby galaxy recession speeds will be inflated. Local galaxies are being pushed faster than average. Measurements that use those local recession speeds to calculate the expansion rate will return a higher than average number, 73 instead of 67. This is the same mechanism the local void hypothesis predicts, but now with a specific, mapped structure identified as the potential culprit. Scientists have not resolved whether the dipole repeller alone is large enough and underdense enough to fully explain the tension. The calculations are difficult, and the structure is hard to map precisely because it is defined by an absence rather than a presence. But the idea that our galaxy's specific location in the cosmic web, near the edge of an enormous void, could be biasing every distance measurement made from our perspective carries a deeply unsettling implication. We might be in the wrong place to measure the universe accurately. And if our location is the problem, the solution requires something that shakes the foundations of physics even more than a new kind of dark energy. Albert Einstein published his theory of general relativity in 1915. It describes gravity as a curvature of space and time caused by mass and energy. The more massive an object, the more it bends the space around it. Other objects follow those curves, and that curving path is what we experience as gravity. For over a century, every test of general relativity has passed. Clocks on GPS satellites run at slightly different speeds than clocks on the ground, exactly as relativity predicts. Light from distant stars bends around the sun by precisely the amount Einstein's equations calculate. Two black holes merging billions of light-years away send ripples through space, detected on Earth in 2015, matching the equations perfectly. General relativity works everywhere it has been tested. The problem is where it has not been tested. Every successful test of general relativity takes place within a galaxy, or between nearby galaxies, or on the scale of a few thousand light-years. On cosmological scales, distances of hundreds of millions or billions of light-years, the equations have never been directly verified. Scientists apply them to the whole universe and assume they hold everywhere. That assumption is built into the standard model. Some physicists believe that assumption is wrong. They argue that gravity behaves slightly differently on cosmic scales than it does on the smaller scales where we have tested it. Their work falls under the label of modified gravity theories. One prominent example is called modified Newtonian dynamics, developed by physicist Mordechai Milgrom in the 1980s. Milgrom proposed that the laws of gravity change when the gravitational acceleration on an object falls below an extremely low threshold. Below that threshold, gravity is stronger than Einstein's equations predict. Above it, everything behaves normally. This idea was originally proposed to explain why the outer edges of galaxies rotate faster than expected without requiring dark matter. Whether it fully solves that problem is still debated. But the same framework makes predictions about cosmological expansion. A separate class of modified gravity theories, called scalar tensor theories, add a new mathematical field to Einstein's equations. This field changes the effective strength of gravity depending on the local density of matter and energy. In dense regions, like near a star or planet, the field is suppressed and gravity behaves normally, exactly matching every test ever done. In sparse regions, like the enormous voids between galaxy clusters, the field activates and modifies gravity's behavior. This is called the screening mechanism. It would explain why modified gravity has never been detected in laboratory or solar system tests. Every test we can run is in a dense environment where the screen is active and gravity looks exactly Einsteinian. But on cosmic scales, in the vast, underdense regions between clusters, the screen lifts. Gravity does something slightly different, and that difference could alter the expansion history of the universe in ways that produce a Hubble constant discrepancy exactly like the one observed. No modified gravity theory has yet been confirmed by data. All of them face challenges, but the renewed urgency brought on by the Hubble tension has pushed the field to take them more seriously than at any point in the past 30 years. Because if gravity works differently on the largest scales, then every assumption the Standard Model makes about how the universe expands and evolves needs to be reconsidered. That is a vast and terrifying rethinking, and it connects to a question that goes even deeper than the physics. What if the rules themselves are not real in the way we think they are? In 2003, philosopher Nick Bostrom published a paper that gained unusual traction outside academic philosophy. His argument was straightforward in structure. Either advanced civilizations almost never develop the ability to run detailed simulations of conscious beings, or almost all advanced civilizations lose interest in running such simulations before doing so, or we are almost certainly living inside a simulation right now. The logic is probabilistic. If even one civilization in the history of any universe develops the ability to simulate minds and chooses to run many such simulations, then simulated minds will vastly outnumber real ones. And any given mind, including yours, is statistically more likely to be simulated than not. Bostrom himself was careful not to claim this proves we live in a simulation. The argument shows it is plausible, not certain. The Hubble tension does not prove the simulation hypothesis either, but it adds an unusual layer to the conversation. Here is why some physicists find the connection interesting. A simulation does not have to be perfect everywhere. A sufficiently powerful simulator running a cosmological simulation would concentrate precision where it matters for the beings inside it. Local physics, the behavior of matter on Earth, in the solar system, in the nearby galaxy, would be rendered with high accuracy because that is where the simulated beings are doing their measurements. Large-scale cosmic structure, the behavior of the universe across billions of light years, might be rendered with less precision, perhaps with slightly different rules, perhaps with parameters that are internally inconsistent at the level of one measurement method versus another. A discrepancy between the early universe measurement and the late universe measurement, where the early universe is a deep past inaccessible to direct observation and the late universe is the region where we actually live and measure things, would be exactly the kind of seam a simulation might show. This is speculative. Scientists are clear about that. The simulation hypothesis is not a physics theory. It makes no specific testable predictions. No experiment can distinguish a real universe from a sufficiently good simulation, almost by definition. But the thought experiment is useful for a different reason. It highlights something the Hubble tension genuinely forces scientists to confront. The model is built on the assumption that the same physical laws operate identically across all of space and time. Every calculation, every prediction, every consistency check depends on that assumption. If the laws vary, even slightly, across cosmic time or across large regions of space, then the model has been wrong in a deep way all along. Every measurement made using the model as a framework would carry that error. The simulation framing is one way to picture what laws that vary across space would look like from the inside. A physical framing of the same idea is called a varying constant. Some physicists have proposed that the constants of nature, the speed of light, the strength of gravity, the charge of an electron, are not actually fixed. They are values that evolved over cosmic time and may still be slowly changing. If constants drift, the Standard Model, built on the assumption that they are fixed, is wrong in a way that would be nearly impossible to detect without precisely this kind of tension between independent measurements. The universe may be telling us something about itself through the Hubble tension. Whether we are ready to hear it depends on how far outside the current framework scientists are willing to look. Some are already there. Physicists have been discussing the multiverse for decades. Multiple universes, possibly infinite in number, each with different physical laws, different constants, different amounts of matter and energy. For a long time, the multiverse existed mostly as a mathematical consequence of other theories. String theory, for instance, predicts an enormous number of possible universes, each with a different configuration of fundamental forces and particles. Our universe is one of them, selected by chance or by necessity. The other universes exist in some meaningful sense, but scientists have never found a way to test for them. The Hubble tension opens a new angle on this conversation. Here is the connection. The cosmological constant, the dark energy term in the Standard Model, has a value that is extraordinarily small compared to what quantum physics predicts it should be. It is smaller by a factor of roughly 10 to the power of 120. That number has 120 zeros in it. There is no known physical reason why the cosmological constant should be this precise. One explanation, seriously proposed by physicists, including Nobel laureate Steven Weinberg, is the anthropic argument. In a multiverse where each universe has a different value of the cosmological constant, most values lead to universes hostile to life. Too high and dark energy rips apart matter before stars can form. Too low and gravity dominates completely, collapsing everything into black holes. Only a narrow range allows galaxies, stars, planets, and eventually observers to exist. We observe the value we do because we could only evolve in a universe with that value. If the Hubble tension points to an evolving dark energy, then the cosmological constant model falls. And if it falls, the question of why dark energy has its specific value becomes even harder to answer without the multiverse framework. An evolving dark energy field, like quintessence, has its own value problem. Why does the quintessence field sit at the specific energy level it does? Why does it change at the rate it does? Multiverse reasoning provides one answer. Among all the possible universes with different quintessence field configurations, we live in one whose configuration produces the right conditions for life, and for observers to notice the Hubble tension. This is uncomfortable science. The multiverse is difficult to test directly. An argument that our universe has the values it does, because observers can only exist in universes with those values, is logically coherent but feels circular. It explains everything and predicts nothing specific. What makes the current moment different is that the Hubble tension gives physicists something concrete to grab onto. If the tension points to a specific type of evolving dark energy, then the multiverse models that produce that type of dark energy become testable in a new way. You can ask, do the multiverse models that naturally generate our dark energy configuration also generate a Hubble tension? If they do, the model gains credibility. Some early calculations suggest the answer might be yes. The implication is vast. A universe that cannot explain its own expansion rate with a single set of fixed laws might be the exact kind of universe you would expect to find yourself in if the laws of physics are not universal constants, but local accidents of one universe among many. That thought changes everything, including the question of how big the universe actually is, and whether the number on every science classroom wall has always been wrong. Every textbook gives the observable universe a radius of about 46 billion light-years. That number sounds precise. It is, but only within the assumptions of the Standard Model. Change those assumptions, and the number changes too. Here is why. The size of the observable universe is not the same as the size of the universe. The observable universe is the sphere of space from which light has had time to reach us since the Big Bang. Light travels at a fixed speed. The universe has existed for about 13.8 billion years. So you might expect the observable universe to be 13.8 billion light-years across in each direction. But space has been expanding the whole time. The point that emitted the light we see today was much closer when it emitted that light. Since then, the expansion of space has carried it farther away. That is why the observable universe radius is 46 billion light-years rather than 13.8 billion. If the expansion rate is higher than 67, as Rees's measurements suggest, then the universe expanded faster than the standard model assumed. A faster expansion changes how far the earliest light had to travel to reach us. It changes the inferred size of the observable universe, and it changes how scientists calculate the distance to the most ancient objects Webb can see. The change is subtle but real. A Hubble constant of 73 instead of 67 shifts the calculated age of the universe slightly downward from 13.8 billion years to roughly 13.5 billion years. Every distance calculated from that age also shifts. A smaller age creates a specific problem. The oldest stars in our galaxy, measured independently through stellar physics, appear to be about 13.2 billion years old. With a Hubble constant of 67, the universe is comfortably older than its oldest stars. With 73, the gap narrows uncomfortably. Some calculations of the oldest star ages push close enough to 13.5 billion years that the stars would be nearly as old as the universe they live in. Stars cannot be older than the universe. A measurement that makes them nearly the same age suggests either the stars are younger than thought, or the universe is older than 73 implies, or both measurements have uncertainties that are not fully accounted for. This tension within a tension shows how deeply connected every cosmological measurement is. Pull on one number, and something on the other side of the web tugs back. The true size of the universe beyond the observable sphere is completely unknown. The observable universe is a bubble defined by what light has reached us. What lies beyond that bubble could be vastly larger, perhaps infinite. The standard model makes no firm prediction for the total size of everything. Some models suggest the full universe is at least 250 times larger than the observable portion. Others suggest it is infinite. If the expansion rate is higher than assumed, then our observable bubble gives us a slightly different sample of the total cosmos. The edges of what we can see represent a slightly different moment in time. A different moment means a different slice of history. And that different slice is exactly where Webb has been finding things that should not be there according to any version of the model. The textbook Big Bang is dramatic but orderly. An infinitely hot, infinitely dense point explodes outward. In the first tiny fraction of a second, a period called inflation, the universe expands at an almost unimaginable rate, growing from smaller than a proton to the size of a grapefruit in less time than any clock can measure. Then, inflation stops. The universe continues expanding, but more slowly. Matter forms. Hydrogen and helium accumulate. Stars ignite. Galaxies assemble. Everything follows a clear, predictable sequence. This story matches observations beautifully at almost every step. But inflation is one of the most poorly understood parts of the entire model. Inflation was proposed in 1980 by physicist Alan Guth to solve several problems with the original Big Bang theory. Before inflation, the model could not explain why the ancient light looks nearly identical in temperature from opposite ends of the sky, regions that should never have been in contact with each other. Inflation solved that by saying those regions were once packed together before the rapid expansion separated them. Inflation also predicted that the early universe should contain tiny quantum fluctuations, microscopic variations in density, that would be stretched to cosmic scales by the rapid expansion. Those stretched fluctuations would become the seeds of every galaxy. Scientists found exactly those patterns in the ancient light. Another extraordinary success for the model. The problem is that inflation requires an energy field, called the inflaton field, whose properties are almost entirely unknown. Scientists know inflation happened because of its effects. They do not know what drove it, how long it lasted precisely, or exactly when it ended. Different versions of inflation produce slightly different universes. Some versions produce inflation that ends more abruptly. Others produce a more gradual transition. Some produce more quantum fluctuations, others fewer. Each version leaves a slightly different imprint on the ancient light and on the distribution of matter in the universe today. Recent reanalysis of Webb data, combined with the Planck satellite's ancient light maps, has found hints that the standard inflation model might not perfectly match what the universe actually shows. The specific pattern of ripples in the ancient light contains some statistical anomalies that certain non-standard inflation models predict better than the simplest version. This is a weak signal. Scientists debate whether it is real or statistical noise, but the direction of the anomaly toward models where inflation lasted slightly longer or produced a slightly different spectrum of fluctuations is consistent with some of the proposed solutions to the Hubble tension. If inflation played out differently from the textbook version, the seeds it planted would have grown into a slightly different universe. One where the early expansion rate does not translate cleanly into the late expansion rate the standard model predicts. One where the gap between 67 and 73 emerges naturally from the physics of the very first moment, rather than requiring new ingredients added later. That possibility makes the Hubble tension something even more fundamental than a problem with dark energy or gravity. It might be a message from the first fraction of a second of existence. And Webb did not stop at hinting. When it looked directly at the earliest galaxies, it found something that stopped astronomers cold. The Webb Space Telescope launched with dozens of scientific goals. One of them was to see the first galaxies that ever formed in the universe. Objects so far away their light has traveled for over 13 billion years to reach us. Nobody expected what it found. In the first few months of science observations, Webb detected galaxies at distances corresponding to roughly 500 million to 700 million years after the Big Bang. That is extremely early. The universe was still young by any cosmic standard. Hydrogen was barely condensing into the first stars. The galaxies Webb found at those distances were far more massive, far more structured, and far more numerous than any model predicted. One set of objects, detected in early 2023, appeared to be as massive as the Milky Way, but existed when the universe was only a few 100 million years old. In the standard model, galaxies build their mass gradually over billions of years through a process of smaller objects merging and growing. A galaxy as massive as the Milky Way should take several billion years to assemble. Several 100 million years is physically too short. Under standard assumptions, there is simply not enough time for gravity to pull together that much matter, form that many stars, and build a galaxy that large. One team that published early Webb results described the situation as galaxies that were too big, too old, and too structured for their age. Their paper estimated these objects were roughly 10 to 100 times more massive than the standard model of galaxy formation predicted for that cosmic epoch. To be clear, this is still an active research area. Some of the early mass estimates have been revised downward as scientists gathered more precise data. Galaxies that initially looked extremely massive turned out to be somewhat less massive when studied more carefully. But even after the revisions, a substantial number of early galaxies remain larger than the models comfortably allow. Scientists have proposed several explanations. Some suggest that the first stars were fundamentally different from today's stars, burning hotter and faster, converting gas into heavy elements at a higher rate and allowing galaxies to build mass more quickly. Others suggest that the feedback processes that normally slow galaxy growth, stars exploding and blasting gas out of galaxies, were less effective in the early universe. And some physicists have proposed that these massive early galaxies are not anomalies in galaxy formation at all. They are evidence that the expansion rate of the early universe was different from what the standard model predicts. If the universe expanded more slowly in its first few 100 million years than the model says, gravity would have had more time to build structure. More time equals bigger galaxies. A slower early expansion rate would push the ancient light Hubble constant measurement upward, closer to 73, reducing the tension. One problem creates another solution. One mystery connects to the next. The galaxies Webb found are not small anomalies. They are large, repeated, statistically significant signals appearing across multiple independent observations by multiple research teams. They cannot be dismissed as noise. Something about the early universe was different from the model's blueprint, and the consequences of being wrong about the early universe ripple forward to reshape everything built on that foundation, including what comes next for the entire human project of understanding the cosmos. Science is often described as self-correcting. That is true. When evidence contradicts a model, the model changes. That is how knowledge advances. What that process looks like from the inside is rarely described with equal honesty. If the standard model of cosmology requires a major revision, the consequences for the scientific community are enormous in practical terms. Every active space mission was designed using the model's predictions. The instruments aboard those missions are calibrated to detect specific signals at specific levels, based on what the model says the universe should look like. A revised model changes what those instruments should be looking for. The Euclid Space Telescope launched in 2023 with a primary goal of mapping the large-scale structure of the universe to measure dark energy. Its observing strategy, how it selects targets, how it prioritizes observations, how it interprets the data it collects, was built around the assumption that dark energy is the cosmological constant. If dark energy is evolving, or if a fifth force is at work, or if modified gravity applies on cosmic scales, the analysis pipeline built into the Euclid mission needs to be redesigned. Redesigning the analysis pipeline of an active space mission is not impossible. It has been done before, but it takes years and requires rebuilding the theoretical framework from which interpretations are drawn. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, faces the same situation. Its dark energy survey is built around specific predictions from the standard model. A revised model could require rethinking which galaxy populations to observe, which statistical tests to apply, and how to interpret discrepancies when they appear. The impact on textbooks is slower but more pervasive. Physics and astronomy courses at every level teach the standard model as established fact, the cosmological constant, the age of the universe, the composition breakdown of 5% matter, 27% dark matter, 68% dark energy. These numbers appear in every introductory course taught around the world. If those numbers change, every textbook changes. Every course changes. Every student who learned the current model learns it, knowing it was a step, not an endpoint. That is not a failure. Science has revised its models before and grown stronger each time. Newtonian gravity was not wrong. It was a special case of Einstein's relativity. The special case still works perfectly well for everyday calculations. The new framework absorbed it and went further. A revised cosmological model would absorb the standard model. The equations that work beautifully on small scales will continue to work. The successful predictions about galaxy formation and ancient light will be explained as approximations valid under specific conditions. But the new framework would go further. It would explain the Hubble tension. It would explain the massive early galaxies. It would explain the anomalously large structures. It would explain why dark energy behaves as it does. The scramble to be the team that builds that framework is already underway. Science is a human endeavor. It runs on data, but it is conducted by people who have careers, ambitions, reputations, and deeply held convictions about how the universe works. The race to solve the Hubble tension is one of the most watched, most competitive, and most personally charged contests in modern physics. The prize, if someone claims it, would rank among the most significant achievements in the history of science. A Nobel Prize would almost certainly follow, possibly multiple ones. Several distinct camps have formed. The measurement camp believes the answer is still in the data. Someone, somewhere, has a systematic error that has not been found yet. This group is concentrated among cosmologists who work with the ancient light measurements. They trust the standard model deeply and believe Webb and future satellites will eventually locate the flaw in the distance ladder. They are running new analyses constantly, applying new statistical techniques, looking for correlations between measurement errors that no one has noticed. The new physics camp believes the model itself needs revision. This group includes Rees and many of the distance ladder researchers, but also a growing number of theoretical physicists who study dark energy, modified gravity, and extensions of the standard model. They are building frameworks, publishing candidates, and competing to produce the theory that fits all the data simultaneously. A third camp, smaller but vocal, believes the answer lies in the large-scale structure of the universe. Local voids, massive walls, the dipole repeller, and the breakdown of the cosmological principle represent the solution in their view. No new physics needed, just a more accurate picture of where we sit in the cosmic web and what that does to our measurements. The careers of dozens of prominent scientists depend on which camp turns out to be right. Papers written in the wrong direction become footnotes. Papers written in the right direction become foundational. Decades of work get either validated or quietly set aside. This creates a specific tension inside the science itself. Researchers who have spent their careers defending the standard model have a stake in it being correct. Researchers who built the distance ladder have a stake in their measurements being accurate. The human incentives and the scientific evidence are not always pointing the same direction, and distinguishing one from the other requires extraordinary honesty from everyone involved. To the field's credit, that honesty has mostly prevailed. Rees's team published the web results promptly, even when they confirmed the tension rather than resolving it. The ancient light teams have published careful analyses of their own uncertainties. Researchers who found evidence for evolving dark energy published it with appropriate caution about its statistical significance. The competition is fierce, the stakes are enormous, and the community is doing it mostly right. The datasets that will decide the outcome are already being collected. Euclid is scanning the sky. The dark energy spectroscopic instrument is still running. Future analyses will combine multiple independent probes in ways that could distinguish between the main theoretical candidates. The answer may come within years, or it may take another decade, but the shape of that answer, whatever it turns out to be, is already emerging from the data. The standard model will not be thrown away. It will be extended. Every successful model in the history of science has followed that pattern. Newton's gravity was not discarded when Einstein published relativity. It became a special case, an approximation that works perfectly well when objects are moving slowly and gravity is weak. Einstein's framework absorbed Newton's and went further. A new cosmological model will absorb lambda CDM in the same way. The pieces that work, the description of galaxy formation, the prediction of the ancient light pattern, the ratio of hydrogen to helium in the universe, will remain valid within the new framework. The new model will explain why they worked and add the missing ingredients that resolve the Hubble tension. Several candidates are being developed simultaneously, and each one looks slightly different. The evolving dark energy models, encouraged by the dark energy spectroscopic instrument results, center on replacing the cosmological constant with a dynamic field. Quintessence models are the leading version. A quintessence field that was weaker in the early universe and grew stronger over time naturally produces a higher expansion rate today than ancient light measurements predict for the early universe. If the field's behavior can be pinned down precisely enough, it could explain the Hubble tension and unify the two measurements under one framework. Early dark energy models add a brief, intense burst of extra energy in the first moments of the universe. This burst would change the sound waves in the early universe, alter the size of the features in the ancient light, and shift what expansion rate scientists infer from that light. Done correctly, it pushes the ancient light measurement upward towards 73, closing the gap. The challenge is avoiding the knock-on effects on galaxy clustering that current models produce. Modified gravity models adjust Einstein's equations on cosmological scales. If gravity is slightly different across the enormous distances between galaxy clusters, the expansion history of the universe would differ from standard predictions in exactly the ways the Hubble tension describes. The screening mechanisms that hide the modification in local tests make this hard to rule out directly. New surveys measuring how gravity behaves on the largest scales could either confirm or eliminate this category. A fourth category involves interactions between dark matter and dark energy, two ingredients that the standard model treats as completely separate. If they interact, exchanging energy over cosmic time, the expansion history would deviate from the standard prediction. Recent models exploring this interaction have found parameter ranges that reduce the Hubble tension without breaking other well-tested predictions. No single model has yet fit all the data simultaneously without introducing new problems. But the field is converging. The number of viable candidates is shrinking as new data eliminates options. What remains after elimination will be the core of whatever comes next. A new model is being built in real time by hundreds of scientists using the most powerful telescopes ever constructed. The Hubble tension is not a dead end. It is the doorway the field walks through to get to the next era of understanding, and the timing of that doorway matters more than most people realize. Every generation of scientists believes it is living through a special moment. Most generations are wrong. Progress is steady, incremental, rarely dramatic. Papers get published, conferences happen, measurements improve by small fractions. The textbooks are revised in footnotes, but occasionally, a genuine turning point arrives. A moment where the old framework breaks and the new one has not yet formed. A moment where the fundamental assumptions of an entire field are on the table. Those moments are rare, and the people inside them often do not recognize them clearly until later. We appear to be inside one now. The Hubble tension sits at the intersection of every major unresolved problem in physics. Dark energy, unknown. Dark matter, unknown. The nature of inflation, unknown. The behavior of gravity on the largest scales, untested. The homogeneity of the universe, challenged. The first galaxies, larger than expected. The oldest structures, bigger than the model allows. Each of these problems existed before the Hubble tension became prominent. What the tension does is connect them. The gap between 67 and 73 is not one isolated anomaly. It is a stress fracture that runs through the entire foundation of modern cosmology, and the cracks it reveals touch every one of those open questions simultaneously. History offers two comparisons. At the end of the 19th century, physics seemed nearly complete. Mechanics, thermodynamics, electromagnetism, all unified into a coherent picture. Then two small problems appeared: the behavior of light at different speeds, the distribution of energy in blackbody radiation, two measurements that would not fit. Within 20 years, those two problems had produced special relativity and quantum mechanics. The entire foundation of physics was rebuilt. In the 1920s and 30s, Einstein's equations predicted an expanding universe. Observation confirmed it. That discovery eventually led to the Big Bang model, dark matter, dark energy, and the standard model of cosmology that now faces a crisis of its own. The Hubble tension is a measurement that will not fit. It is the third small problem in the history of modern physics to resist resolution by existing tools. And the pattern of what follows small problems that resist resolution is well established. The resolution comes from outside the current framework. This time, the resolution may bring with it a complete picture of dark energy, a new understanding of gravity at cosmic scales, a revised history of the universe's first moments, and possibly the first hints of physics that connects cosmology to the quantum world in ways that have never been achieved. That is not guaranteed. It might take longer than anyone hopes. The answer might require instruments not yet built, mathematics not yet developed, ideas not yet imagined by anyone currently working in the field. But the tools are better than they have ever been. Webb is still running. Euclid is scanning. The dark energy spectroscopic instrument is still collecting data. The next generation of ground-based telescopes will come online within years. The volume of high-quality data arriving is unprecedented, and somewhere in that data, the answer is already there. A Nobel Prize winner looked at the numbers and said the model is broken. The field listened. The race to build what comes next is the most exciting contest in the history of human knowledge. We are alive for it,